Okay. Open. Slideshow. Current slide. All right. So IIR filters is another, let's say, family of filters, but here the impulse response is infinite. So usually this is achieved by either having like a function, like an expression, or by using a recursive structure. By a recursive structure, basically we have a feedback. Like the output will rely on past values of the output. So here is the outline. We'll talk about some general information, some basic comparison. We'll see that FIR has advantage of simplicity and always stable. IIR a little bit complicated. Sometimes it's not stable, but assuming two filters of the same order, IIR will do a better job when compared to FIR. So you need less coefficients when compared to FIR. And some implementations and examples of IIR filters. So the infinite impulse response filters are composed of several decaying exponentials. So that's one of them. One of the structures, you have e to the power minus alpha n u of n. So you have some decaying exponentials and decaying for stability, that's for sure. And they are also called recursive filters, given that they use feedback. So again, you have it either an expression or with a feedback method in order to bypass a longer convolution process, which can happen due to infinite nature. So it can be recalled that we used to do full convolution process to FIR filters. And yeah, it's saying that to have a good representation, you can use the recursive structure. Okay, so here is an example, FIR, simple system like that. You have input, filter with the finite number of coefficients, and you have the output. Here, yeah, you may have some certain number of coefficients, but you have a feedback, and that will always, let's say, give you values for y of n with respect to x of n. Okay, some characteristics. Here is the general expression of IIR filter. If you remember, this is the part of FIR. You have something like this, as band limited, k equals 0 to n, and these are the coefficients for the FIR filter. However, when you add this version of delayed versions of y of n, then you will get this IIR structure. Okay, so it is characterized by the following. So you have feed-forward coefficients that's related to the FIR structure. And you have n+1 feedback coefficients, that's from A of k. And the values go from 1 to A of m. And so the order, which is equal the maximum of n minus m. Again, you just look at the maximum delay, and that's going to be the order of the filter. So an impulse response, h of n, which is an infinite IIR. So h of n here, you cannot just simply say it's 1, 5, 10, and that's it. It's just infinite, like it becomes like a function of, let's say, the A's and B's. And we'll see that later when we talk about the transfer function, h of z. Some comparison. So FIR, it is finite. After a certain point in time, you will have zeros everywhere. It has good performance. It is more powerful when compared to IR, but will become more complex. It is always stable. That's one of the advantages of FIR, and we'll show an example why it is always stable. More straightforward to design, but less flexible. However, IIR is infinite, so there are always values there. It will decay over time. It will never reach zero, but we give an approximation to make the filter realizable. It is less powerful, but less complex to implement in real time. So here it has better real-time application using microcontrollers. It is not always stable, so you have to be careful when designing them. And you can, let's say, have more flexibility when working with the parameters. If you want to compare the structure of IR and IR, here you have the values of A's and B's, and if IR is always constant set of values of, let's say, B of K's. If you remember this one, I think from the first or second lecture, so that's the structure here. Whenever you have delayed versions of Y of N, that's an IIR filter. That's it. That's to put it simply this way. That's an IIR filter. It always relies on past values of Y of N. All right. Okay. So when it comes to transfer function, basically the Z transform of like the structure given there. You don't have to memorize this, by the way. It just show you that you have these coefficients. And again, the order is the maximum of the highest power, B of N and M, N and M. So due to the recursive feedback, a causal IR filter cannot have a linear phase. Let's not worry about linear phase and stuff. But yeah, it is causal. Phase usually have something to do with delays. When you have nonlinear phase, like there are issues with like variation delays. So therefore, the denominator of Z transfer function can never be a single coefficient and will have the following layout. So it is summation. Actually, this one is derived from that one there. And then take Y of N. Then you have the shifted versions of Y of N taken there. Then you take Y of N as a common factor, and so on and so on. And you will end up with having this one. Again, let's not worry about this structure. The poles here, you have to be careful because the values, the coefficients here will determine where the poles are. For stability, the poles have to be inside the unit circle in the transform. So this means there can be poles placed off the origin. And that will cause for stability. Okay, so the difference equation will have a feedback. Again, that's the feedback part, weighted by A of K. The transfer function H of Z can have poles and zeros off the origin and probably outside the unit circle, provides more flexibility in the design process. A differentiator? Where did you see that? Okay, so basically a differentiator, like if you have X of N or X of T, communication system. Okay, so it is something like this. You multiply by S. That's how they model it in Laplace domain, or D over dt. And you will get X prime of T. That's a differentiator.
Because like in some questions, it's asking is it linear?
Okay, so a differentiator, you have it like this, X and X of T. So is it linear? You want to apply the linearity principle? You have X, or maybe let's go after the lecture. Okay, that's an assignment.
Yeah.
Okay, it is linear. All right. And transfer function H of Z can be both can have both poles and zeros off the origin and maybe outside the unit circle, so which provide more flexibility in the design. In general, IR filters require a smaller order than FIR. See, that's probably one of the advantages to satisfy the same set of specifications, probably in frequency response. So for the same order, IR filters produce better response when compared to FIR. And that's thanks to the feedback, actually. So having poles outside the origin means that unless careful design procedure, the system will be unstable. So that's some information about IIR filters. So you have flexibility in design when compared to FIR. All right, so stability for causal IR filters. A causal IR filter is said to be stable in two conditions. Stability actually has something to do with the magnitude or amplitude, like with all time. The summation should be less than infinity. And I think we've done that in the signals system. Let's say you have e to the power minus n and determine if this system is stable. So you have this one, amplitude, let's say from 0 to infinity. And using some certain set of tables, you will find that it has a certain expression and that is bounded. That is, let's say, less than infinity. Will not go to infinity. So the impulse response should be summable and bounded. And for stability, that's something for related to the poles of the system, not a or a to the power n. All right. So the inverse transform for FIR is usually related to partial fraction expansion, and we have these exponents a to the power negative n u of n, something like that. And that, if you remember, in z transform will cause to have like 1 over z plus a. We'll check the table, something like that, z plus a. All right, let me see if I got that. A to the power n. I said a to the power u of a to the power n. Oh yeah, z plus a, so there's z minus a. Yeah, more or less. Yeah, let's stick to the tables. So I'll just remove that one so as not to get confused. So using the tables, so this one is basically linearity principle. Z transform, it's, let's say, outside, you have, becomes outside the coefficient, so x of z and plus is plus, and you have the weighted coefficients there. Delay in time domain will cause to multiplication by exponent in z domain. Convolution in time domain will cause into multiplication in the frequency domain. Delta of n z transform is 1. You have shifted delta, you have z to the negative n. And this is the most common one. So usually when we apply z transform, we want something like this. When we do that, sorry, the partial fraction expansion, I want to get something like this. So I can use the tables to get that expression. All right. So here is an example here. Consider a system whose system function as h of z b naught plus b1 z of minus 1 over 1 minus a naught z of negative 1. So the input to this system is the unit step function, and the unit step function has this z transform, and it does ask find y of n. So from the properties, y of z equal h of z times x of z. So you'll get this expression here. Now it's asking for y of n. So to do the partial fraction expansion, we have it, it will become a over 1 minus a1 z negative 1 plus b over 1 minus z negative 1. And then you do the cross multiplication, and it will be a function of b naught and b1. I'll avoid that in the exam, like you'll have these numbers. However, this question actually is solved here. So yeah, as I mentioned, partial fraction expansion. Now the goal is to find the values of a and b. So once they are found, you can find the values by bound, and you've done that in signal assistance, I believe, the inverse did transform. So you have some constant over 1 minus a1 z negative 1, and you go here, and this is the constant. So you will have that constant to the power n times u of n. All right, so here are the coefficients. And notice there should not be any z here, it's just the constant value. Same thing here. And that will be the inverse z transform. So this is the value of a of n. Here, this is the constant. This is a, and this is b, and that's a1, and that's the value there. That's for b. There's no coefficient there. Or actually, it's a 1. Yeah, this one here, it's 1. So that's why b by this coefficient. And the worksheet, I think, I think we will have time to solve questions from the worksheet. So how to do the inverse transform, factor the denominator, something you've already done. So create a partial fraction expansions and express it in the inverse transform. Actually, this is a general formulation of how partial fraction expansion works. But basically, that's a1 over 1 minus p1z negative 1 plus a2 1 minus p2z negative 1, and so on. and then find the coefficients. Actually, this one's not even necessary. Find A1, A2, etc. And then your output will basically finding the values of P of K. So A of K, A1, P1, P1 of N, A2, P2 of N, and so on and so on. All right. So the main target is to find these coefficients. I won't say limitations, but some complications may happen during the Z transform procedure when you have repeated roots or repeated poles. So this one is applicable for non-repeated poles, but we will avoid that. Like in our assessments, we will never have this case of repeated poles. The denominator must be factored form, which requires pre-calculations, means that I can go from something like this. So this is like a polynomial of second degree. I can factorize it into something like this. So this is the challenge of partial fraction expansion. So the partial fraction expansion method is applied only if the function is proper rational function, such as the order of the denominator is greater than the order of numerator. It means that the power here, like that's a first order polynomial, that's a second order polynomial, and that's where I can apply the partial fraction expansion. If the order here is higher than this, I cannot do that. I have to do long division. I will get something outside, then I apply the partial fraction expansion. It's not a very straightforward procedure. So in case the function is not in the proper function, then it should be written in the form of polynomial and proper function before applying the partial fraction expansion. So let's do an example here. That's a typical example you may face in the exam. So use the inverse Z transform method in order to find the differential equation x of n from the Z transform function x of z by given this expression below. So I'll take the expression, take it to the whiteboard. So there. Okay. First, can we factorize this? Calculator. You can do it with the calculator. Because at the end, I want to have it a over 1 plus minus, let's say, p1 z negative 1 plus b over 1 plus minus p z negative 1. I said plus minus because I don't know the signs. So we are not used to see this one. And what coefficients you need to fill? Like to find the roots for this. What will be the values you put? Okay, if you multiply by z squared, you keep that order. Because think about it this way. If you multiply this one by z squared, and you multiply this by z squared, it's like multiplying by ones, huh? Then you have z squared minus 0.3 z minus 0.403. And then you factorize it. And then you have something plus z, something plus z. Take z out from each one of them. So this one, you will have like z plus the first root, r1, z plus r2. Okay? Take z outside. So you have 1 minus r1 z negative 1 في 1 minus r1 minus ولا plus. I'll put them both plus r1 z negative 1. هاي أخذنا منها z وهاي أخذنا منها z square. It will cancel with that one I already have. So you fill which were values then in this case? 1, negative 3, negative 4 or 3. You see the point? You see my point there? So in the calculator, apply. So I have A and show. Okay. So what will be 1 minus plus or minus minus 0.8 1 plus 5. Okay, 5 ولا انتوا approximate 0 كان عندنا 4 او 3 يعني لو كانت 4 لحالها I agree with you بس كان عندنا 4 او 3 وهاي 8 يعني 0. اوكي I will get these values. خلينا نتأكد 1 ولا لا في عندنا 0 3 0 2 minus 5. اوكي يا هذا الرقم مش عاجبني. يا let's forget this 3. 8 و 5 أريح. second. All right. All right, so cross multiply. You will get A 1 plus 0.5 Z negative 1 plus B 1 minus 0.8 Z minus 1. That should equal what? 1 minus 2.1 Z negative 1. تمام? So how to solve it? Just a second. I have an important call. Just give me a minute. Okay, let's continue. Yeah, sorry for the. Okay, so what will be the best way to solve this? How can I make this one 0? How can I make this one 0? Okay, it's easy actually. Substitute the values of Z, right? So what will be the value to make this one 0? Negative 2y. Negative 2. Okay, negative 2, it was Z alone, but this is the negative 1. Easiest way, see this coefficient? Is the same value but reverse the sign. Why? Because the number by its inverse, because 1, and I have 1. I have plus. So let's make it clear. So add, I want to get rid of A, add Z equal negative 0.5. Why 0.5? Because I have 0.5 times 0.5 inverse, any number by its inverse, it's 1. Then I have plus, that's a negative, so they will cancel each out. So I will get 1 minus 2.1 negative 0.5 equals, this will become 0, plus B 1 minus 0.8 times 2, which is negative 0.5 reversed. All right, so I will have 1.6 minus 1, that's 0.6b. And I have, so this one is 2, and I have plus 5.2. Then b equals 5.2 over 0.6. So it's going to be a large value, 8.6. That's b. Now what about a? At z equal how much? 0.8. I will have 1 minus 2.1 times 0.8 negative 1 equal a phi 1 plus 0.5 0.8 inverse, and this will become 0. So what is 0.8 inverse? It's 10 over 8, right? So have you done the math for the first one? Negative 1? 625, that equals to a 1.625. So a equal negative 1. All right. So in this case, I will have, go back to my original function. So I will have negative 1 over 1 minus 0.8 z negative 1 plus 8 point, what was the value? 6. 1 plus 0.5 z negative 1. So to apply the inverse, this one will be negative 0.8 to the power n u of n. صح? We go back to the tables. I have this one here. So 1 minus, so it's going to be positive a to the power n. So I have the negative sign is outside the exponent, make sure of that. 0.8, that's the coefficient, to the power n, plus 8.6 negative 0.5 u. Dash negative 0.5 because minus. Tamam. I believe the question is solved in the slides, hopefully. Something is wrong. You gave me wrong coefficients. A should be 2. Or B. Okay, let's at least look here. A 1.0.5 negative 1. Or 0.8 plus 0.5. Okay, so my expressions here are correct. This is correct. A 1 point negative a z negative 1 minus 8 positive 5. اوكي هاي صح عندنا برضه نيجاتيف 1 صح عندنا مشكله بالاثنين Let's go back here. النهاية عندنا negative 1. It's correct. نشوف هون. All right. هي 1 plus ولا 1 minus؟ 1 minus. لا مش راضي يطلع 5. لازم تطلع 2 هاي 5.2. 2.6. لحظة شوي. هاي let's see. كنسلنا هاي 5 ضرب 2. negative 2 sorry. صارت negative plus 2.6. 1.6 plus 1 2.6. 2.6 صارت 2. all right. شايفين could happen. All right, so instead of 8.6 we are getting 2 actually. So this is 2 and I will have 2 there. So here is the answer. There you go. 2 by negative 0.5 to the power n u of n and negative minus 0.8 u of n. تمام? All right, some examples about IIR filters. You don't have to memorize them, but just tells you some information or characteristics about each one of them. So for example, we have the Butterworth filter, has the advantage of having a flat response at the pass band and the flat response at the stop band, smooth transition, quite sharp. So the magnitude frequency response is monotonic in both pass band and stop band. Monotonic means that there's no variations like this. It's either increasing or decreasing. The response is said to be maximally flat because of its initial flatness with a slope of 0 at DC. So it is flat here. Increasing the order n of the filter gives a sharper transition. So this transition from here to there, when you increase the order, the filter will become sharper. So this is a good filter actually, like in terms of selectivity, and there is no ripple. There are no variations at the pass band and the stop band. Another filter, Chebyshev filter, that's Chebyshev type 1. It has, these variations at the pass band. However, when you compare this one in terms of transition compared to the Butterworth, this one is sharper, but has this issue. So there are trade-offs always. Like if you're looking for a sharp filter, this one is better. If you're looking for a filter that has good smooth pass band, this one is a better one. So magnitude frequency response has equiripple in the pass band and monotonic in the stop band. Increasing the order of n increases the number of ripples in the pass band, gives a sharper transition and improves the stop band attenuation. For a given order n, Chebyshev gives a sharper transition than Butterworth compared to the previous one. I think these are the statements that are important that you might be questioned and in a multiple choice question in the exam. Like which one has a sharper transition, Chebyshev or Butterworth and so on. So Chebyshev has a better transition. This one here, that's a Chebyshev type 2 filter. Like see, in this one here, the ripple was at the pass band. There, the ripple is at the stop band, flat, same sharpness. The magnitude frequency response is monotonic at the pass band. Monotonic again, there is no variations, and has equiripple at the stop band. Increasing the order of n increases the number of ripples in the stop band, gives a sharper transition, improve the pass band ripple performance. For a given Chebyshev 2 gives a sharper transition than Butterworth. Actually, in both Chebyshev, sharper transition than Butterworth. Elliptic filter. So the magnitude has like a small ripple here. Same thing for there. Magnitude frequency response has equiripple in both pass band and stop band. Increase the order n increases the number of ripple at the stop band. So increasing the order, you'll have, let's say, more ripple. Same thing here. And pass band gives a sharper transition. For the same order, elliptic gives a sharper transition than both Butterworth and Chip. Notice like from the Butterworth has good transition. Chip 1 and 2, they have better or sharper transition. Elliptic is even sharper. So focus into this point, like when it talks about sharpness or better transition. Some detailed comparison between both filters. IIR filters less stable. We have issues with stability, like might have poles outside the unit circle. Has less memory requirements because with less number of coefficients, I can achieve the same performance like FIR or less order than FIR due to the presence of feedback loops. More computationally efficient. Examples: Butterworth, Chebyshev 1 and 2, and elliptic. Well, let's not worry about application. There are many actually. For FIR filters, the transfer functions do not contain any poles, so hence it's always stable. We'll show an example why FIR is always stable. Requires more memory than IIR to get the same performance. Less computational efficiency. And an example there is a differentiator. Example, audio and control systems, medical devices. And that's it for this lecture. Okay. Let me solve an example of FIR filters and why it is always stable. So let's have an example of any FIR filter that you may think of. So h of n equals 2 delta of n minus 3 delta of n minus 1 plus 5 delta of n minus 2. That's minus 1. So what will be h of z? 2 minus 3z negative 1 plus 5z negative 2. That's the transform. All right. So how to find the zeros and poles for this function? Multiply by z square over z square. So you have 2z square minus 3z plus 5 over z square. How many poles? As a unit circle, 2 poles at the center. Even whatever the filter it was, you will always have a z to the power n here. So that's why it is always stable. Your poles are always at the 0. And you can play with the variations of the zeros of the function or the transfer function. And from there, like you can play around with the phase transition and stuff, but the filter, you guarantee that it is a stable filter. All right. Let's see in the tutorials there if we have any good examples about IIR. So I believe that's 5. Okay, there you go. Consider the following transfer function given below. Apply the inverse of the transform. We've done the same exact example to determine the differential equation. So yeah, a over 1 minus 0.5 z, b over 1, and then find the coefficients of a and b, then apply the inverse Laplace, pretty much like the example we did before. Determine the required input x of z to the system if the desired output is given by y of z. So you have y of z, you have h of z. How to find x of z? Okay, what's the relationship between x, y, and h? Yeah, exactly. So you have y of z, you have h of z, do division. That's it. And you'll find out that x of z is simply 1 over 1 plus 0.75 z negative 1. Because this one and that one will cancel each out. Okay, give the following differential output equation. Use a z transform summary table to convert this into a z domain y of z. Okay, how to do that? Use the table. Find the convert this into y of z. So this is y of n. What is y of z? اوكي وين التيبل هذا؟ بدكم تيبل بعد so this one is 1 over 4 over 1 minus half u of n. Sorry, half z negative 1. What about this one? The part. Okay, let me take the question and do it at the whiteboard. The whole thing. Copy. All right. Okay, so in Z transform, a to the power n, u of n, 1 over 1 minus a, z negative 1. Okay, so the first one is going to be 4 over 1 minus 0.5, z negative 1. What about this one here? Okay, what do we see here? Shift. So we have shifting in time domain. Shift in time domain, x of n minus n naught. بالZ domain راح يكون z to the power negative n naught x of z. بالتابل هاي افتح التابل. lectures IIR filters. All right, so how to deal with this? So we've seen that there is an expression for that. So first, assume that there is no delay. So you will get minus 2 over 1 minus 0.25 z negative 1. So multiplied by I from the delay part. Other? Okay. So we've done that. From the Z transform, we determine what type of filter this and why. From the Z transform, determine what type of filter is this and why. I will say a differentiator, but no, I don't think you will know what differentiator is. All right, let's see like the answer. I would say it's a differentiator. Solution. Let's see. وين السؤال؟ it's an IIR filter. From the presence of poles. Okay, لا أنا ما بعطيكم what type of filter. Determine if this filter is IR or FIR. يعني I'll give you choices. لأن there are different classification of filters. Low pass, high pass, finite, infinite. So okay. فكرنا بعيد كثير إحنا. So all right. From the Z determine the poles and zeros and comment on the system stability. البولز سهلين على النص وعلى الربع. Stable. The zeros you have to solve. يعني you have to cross multiply طلع الاكسبريشن النيوميريتور بعدين يطلع معك الزيروز. So quadratic formula zeros poles هي هم النص والربع الزيروز موجودين فوق. Alrighty. So IIR pretty straightforward. Again, I will upload this one later إن شاء الله.
كيف فلتر IIR؟
لأنه expression mathematical formula. لو كان FIR بيكون coefficients 1 2 3 finite number of components. هون if you look at it like even in the time domain هون for any value of n there could be a value for the filter, so it's infinite, goes forever. ال FIR بيكون coefficients given constants. بكون function, you have an expression, exponent or unit step. يعني unit step احنا what do we know about unit step? From 0 to infinity, and you have it like this. بس ايش انه half to the power n after long time it will die out, but still there are values. No matter how small, it's not zero, but very close to zero. All right. So let's stop sharing. Okay, stop the recording. بدك تشوف الديفرنشيتر